When referring to this unit, you're going to want to take a look at Chapter 12 in your textbook. You are actually going to be designing your own labs where you are going to look at several different physical characteristics that are connected to the basic property of intermolecular forces. So let's first talk about inter and intramolecular forces. So we're going to abbreviate these forces as IMFs. There are intermolecular forces as well as intramolecular forces. So the first thing, a definition of the intermolecular forces are the forces of attraction between molecules or atoms of a substance. So if a material has a greater intermolecular force, then the attraction between those molecules is going to be greater. So if I had two different molecules, the forces would be greater and those molecules would want to stay together. We're going to be continually learning about the electrons in an atom because it is ultimately the electrons that are interacting to determine the strength of the intermolecular forces. So when we have two molecules that have an opposite charge, because opposites attract, the greater the difference in charge, the greater the intermolecular force. So you can kind of compare it to magnets. If the magnets are very strong magnets, they have a greater difference between their positive and negative, and so they're going to have a stronger pull between those magnets. So let's define the difference between intra and intermolecular forces. Intramolecular forces we've actually talked quite a bit about. Those are going to include the different kinds of bonds that we've looked at already. So it's going to include ionic, covalent, and metallic bonds. Those are intra. Intermolecular forces are between the molecules. So a good example of this would be an intermolecular force would be if I have a molecule of H2O and then I have another molecule of H2O, those molecules are going to interact with each other. So this one's going to interact with this one. Those are going to be intermolecular forces. So intramolecular forces we've talked about ionic, where we have two oppositely charged atoms attracting to each other. We've talked about covalent, where the atoms share the electrons. And we've talked about metallic, where those electrons are all being passed throughout the entire compound of that metal. And so that's the reason for that electricity flow, as well as the malleability of the metals. So intermolecular forces we're going to be talking about are going to include dispersion forces, dipole-dipole, as well as hydrogen bonds. So here's a first example for you of these intermolecular forces. This is helium. Helium atoms are very weakly attracted to each other. Typically gases have very weak attractions, and that's why those molecules can just move all over and they spread out and they can be compressed and squeezed together. So there's very weak intermolecular forces between gases. And so helium is a gas at room temperature because those molecules are not attracted to each other, and so they stay pretty far away and they move randomly throughout space. So that would be an example of a very weak intermolecular attraction. So there are different names for the different intermolecular forces that we're going to see. One of them is a dispersion effect. We've already mentioned once the HOBEFINCI twins. These are molecules that are attracted to each other. They are going to exist as diatomic molecules, so they have two of them. So H2 is an example, O2 is an example of these. And basically what happens is there's just a shift in the electrons. Now this is a pretty weak attraction. Again, they're gases, and this attraction is fleeting, so it comes and goes. Another example is a dipole-dipole attraction. These are a bit stronger, and these are the attraction between the opposite charged sides of a polar molecule. So a good example of these is water molecules do dipole-dipole bonds, where one side of the water molecule has a little bit of a positive charge, which we can see right here, and then here and here end here, and the other side has a little bit of a negative charge. And that's because the larger oxygen atom attracts the electrons to it because there's more protons to pull on it. And so since it does that, that side of the molecule gets a little bit of a negative charge, and that's called a polar molecule. Well, when you've got opposites, a positive and a negative, attracted to each other, then they're going to have that attraction, and they're going to have a little bit stronger of an intermolecular force. So here's an example for you. Helium, we said, had weaker forces. Now water has stronger forces within it. And so water molecules are relatively strongly attracted to each other. And like I mentioned, they have that dipole-dipole attraction. A lot of times we call this a hydrogen bond because the hydrogen and the oxygen attract to each other. And so the boiling point and melting point of water are a lot higher than those of most liquids. The melting point of water is 0 degrees Celsius. The boiling point is 100 degrees Celsius. And it's all because of the intermolecular forces. We're going to see as we do labs that other materials melt and boil at lower temperatures, have lower intermolecular forces. And then we have things like our metals. Metals have very strong intermolecular forces and intramolecular forces because of those metals all exchanging those electrons. And so they have a very high melting point and even higher boiling point than water does. So my third example is the highest intermolecular forces between those atoms. And the example is going to be carbon atoms bonded together in the form of a diamond. And these atoms inside of diamonds are held together by the strongest kind of intermolecular forces that we see, which are covalent bonds. These are intramolecular forces, and they're very strong intramolecular forces, which means that it's going to make a diamond the hardest material on our planet. And so you can see they have extremely high melting points and boiling points there because in order to pull those molecules apart, in order to go into a liquid form or a gas form, you're going to need a lot of energy to do that because of how strong that connection is between those molecules. There are actually a lot of different physical properties that are going to be affected by these intramolecular and intermolecular forces. And some of the ones that we are going to look at are going to include density, surface tension, the compression or the squeezing ability, the ability to squeeze a material. Fluidity and viscosity are similar, but fluidity is going to have to do with gases and how they disperse. Viscosity is the ability to flow for a liquid. We're also going to look at adhesion and cohesion. Adhesion is going to be the attraction between molecules that are going to be this different materials, whereas cohesion is going to be that attraction between the same. So if you think of as co-captains, it'd be two of the same materials. I've already mentioned melting point and boiling point and how those can be affected with comparing water to carbon, and then also evaporation rates of liquids. If a liquid has a greater IMF, it's going to evaporate slower. If it has a lesser IMF, it's going to evaporate faster. So finally, we're going to see some general trends when it comes to some of these different properties. If a material has weak inter and intramolecular forces, it is typically going to have a low melting point and a low boiling point because it doesn't take a lot of energy to make those molecules go from being tight together to spreading out and flowing in a liquid or a gas form. They also will have a low surface tension, which means that the material is, if it were to form a little bubble, the liquid of those molecules connecting to each other, that little bubble is going to break apart very easily. And then If the intermolecular forces are weak, it's going to evaporate very quickly. Remember, evaporation is going from a liquid to a gas, so if there's not a very strong force to hold those molecules as a liquid, they're going to easily float away as a gas and remove and separate themselves from those intermolecular forces, from those other molecules. The opposite holds true if there's strong intermolecular forces. High melting point, boiling point, high surface tension, and a low rate of evaporation.